Yes, started recording. So welcome once again to the 8th session for this data structures algorithm using algorithm. So this in this session we're going to talk about time complexity. So to do that, first I'm going to share one sheet with you which going to work upon throughout this session. Let me You may download the session and download the particular sheet, and then you can work upon it later, but I will be working simultaneously right now. So let me share the screen, and you can if you have any question during this time, you can start typing in the chat box. So let's share the screen. Okay, so let's now Okay, so today what we are going to focus upon is time complexity, basically how to calculate it for a given program or particular function, how to calculate it. So we're going to see for this one session multiple different type of questions which we're going to use and try to understand how different terminologies as well as how different methods using which you can find the time complexity. So before that, there are few things that we should know about. Usually we focus on two-part series. So in the part 1 we are going to focus on this method, that is frequency count method. So we will try to understand the number of computation based on the input size, based on which we are going to find the time complexity. And then in part 2 we will go actually into semantics of the time complexity, that is big O, there's omega, then theta. So that will happen in the next session. So now let's get start with this thing, and if you have any questions with respect to it, you can ask me through the chat box. Another thing that I would emphasize, I just put a link in the chat box about this same data sheet, and I'm going to use it upload in the YouTube channel as well, and the NPTEL will also give it to you, so which you can use and practice. Okay, so let me start with the first question. So why time complexity is needed, and why do we it's an important matter specifically in an algorithm. So to tell that, we can say, to understand that why time complexity is useful, we should know that ideally which algorithm is fast or slow, and how do we define it? Basically based on the number of inputs. So if input is high and still the algorithm working fast, that is our ideal condition. But if it is slow, like as the inputs getting higher and higher and it is getting slow, this is not ideal case for us. So we should identify such cases. So whatever the algorithm or whatever the program that you're going to write, even for computer programming or in general sense while developing a software, we always aim for this fast part. We are not aim for slow. So for that we should get a rough idea, some approximation. Time complexity that we are going to identify is basically approximation that how this particular algorithm will work during this execution time. So understanding, that's why time complexity is very important concept while learning about the algorithms. So this is not restricted to any particular language, be it C++ or Java or Python or anything. The concept apply the same. The semantics may differ, but over a period of time, the logic is same. So we are focusing much on logic. We are not focusing on semantics. So whatever the code that we are going to see, it's called pseudocode. This pseudocode can be written at any point of for any language, and this will be applicable whole true for any programming language. Okay, so let's start with the first algorithm, that is so this algorithm 1. So what it actually doing here is it has a sum function. It is taking an array, and this is the size of array. And for this we need to know the time complexity of a function. So that means how, based on the input size, how good the function will work upon. So let's see. So in this we will see usually from the term of statements and the unit of time. So you should know the term called statements and unit of time. So one statement, we are approximating that it will take order of one time. It's not big O, it's order of one time. So when we say order of one, that means it take 1 unit of time to execute one statement. So for example, when we are saying s equal to 0, it is taking 1 unit time because of one statement. Now when it comes to return s also, it going to execute once. So that's why it is going we will tell it as 1 unit of time for the return s statement. But when it comes to for loop, it is not going to like that. Since a loop statement, it is iterative, so we have to see for how much duration it will take the time. So in general, we all know to for loop how it will start. So suppose n value is n 5, so I will be start from 0 1 2 3 4 5. So here 0 to 4 it will work properly, but when it comes to 5 it will not work. So during this next time only it will run for 5 times. That means it is n times. So it will run for this statement particularly run for n time, but this will run for n plus 1. Why this? Because of this condition, I less than n, because it was going to check for 5 less than 5 or not. So this will act as a sixth statement. So that's why n plus 1. So if we combine and check, see that what is the time complexity for this algorithm sum, it will be 2n plus 3, and it's basically a time function for this. But we are not going to make equations for it, so we want a more simplified version. So we usually see the degree of n. So usually in this case we will say it as it's order of n. We are not defining any notation here. We are just, for now we are saying O, which is O, this going to be saying as order of n. Okay, this is one aspect. Now something called as space complexity. Space complexity will usually refer it as the variables that we are employing in the particular algorithm. So in this, the variables will be a, that is array, and then we will have n, we will have s, we will have I. So array has a size n, because that's what we are it is getting as a input. N is a variable, so we will give a variable as unit of space 1. Similarly, for any variable we'll give 1, so be it s or I. So total will be n plus 3. So space complexity will be also order of n. So we are not focusing much on equation, we are much focusing on the degree of the polynomial or the equation that we are getting. The more example we will see, we will get more and better understanding. Okay, so let's take the another algorithm here. So in this algorithm is basically addition of a matrix. Okay, two matrices. So in this we are getting one array B as a second array and the size. So we are assuming both have same size. Now since to go by this, ideally it will the first loop, this is called nested loop. So obviously the first loop will run for n plus 1 time. So it is running for n plus 1 time because the 1 plus 1 time usually will tell that that's a wrong condition. That after this it can't run. That's why. So if it is running for n plus 1 time, it will run for n time. This statement also for run time. So we targeted the whole for loop for the ith for loop, but we have to check for jth for loop as well. So this loop particularly also run for n plus 1 time. Why? So it will start for 0 and will check till n is less than n or not. Since it is false, it will get out of that loop. So in that also, if it is running for n plus 1 time, the statement will run for n times this statement. Okay, and usually over the in the next few section we will focus that our focus should be of this statement, this particular statement. We are not interested that much in the for loop statement, how much time taking, because this is the actual computation. That Cij is will be the actual computation which we are concerned about, right? So if we take it out and try to sum it up, so we will find that it has 2n square 2n plus 1, and this is the time function we are getting. And if we have to summarize it, or if you have to say in a summarized way, we will say it's order of n square. We are removing this 2, we are removing this 2n plus 1, but just by looking this we know that it will be for an input size n, it will run this program for run for n square time. Okay, that's what it meant. And you can also trace it out. So for example, if I have, how you can trace it out is you can take I and j. So when I equal to 0 and let's say n equal to 5, so for j will run for 0 1 2 3 4. At fifth condition it will false. Then again it will run for I equal to 1, again it will run for 1 2 3 4. So such that it will go till the fourth part, and then it will go 1 2 3 4, 0 1 2 3 4. So here it is running for 5 times, again 5 times, again 5 times. So if we find out, it will be actually a n square. So if 25 times it is running. So that's how you can trace it out, how a particular algorithm time complexity can be found out. That's how you should trace it out. Okay. So let's go to so if you have any question with respect to this, if you are not able to understand, we are following, yeah, please type that in the chat such that I can see and I can reply to your answer questions. Okay, so we have seen till now for O of n, this is O for n square, and this is L, this is what going to see for multiplication of true matrices. So these type of problems that you usually generally solve for computer programming, right? So where it involves 2 loops, 3 loops, 1 loop, and we will see variations in loops as well. So we will check those things and we'll see that how the time complexity actually differed in such cases. Right now we are taking the simple basic examples. All will be basic example, but the variations will be quite a lot. Okay, so again to trace it here, to understand that how much time, we will say usually for multiplication to matrix we usually say that it's order of n cube, but why? So for that we should trace it out. So how we can trace it out here is, we'll start with topmost loop, then we'll go inside one loop, and then we'll go for inside one loop. Okay, so for for ith loop, how we will see is, it will run for n plus 1 time. If it is running for n plus 1 time, it will run for n time. This statement also run for 1 time, this statement for 1 time, this will also statement will run for n time. Now once this is done, then we will go for jth loop, and for the jth loop again we are going to check how much time it will take. So the for loop particularly will take one step more extra to check the condition, particularly this condition where this I is less than n or j is less than or not. And then it will, since it will go n plus 10 times, so whatever inside this jth loop is there, that will run for n times. So we can write it as n times n times n times. Now there's another loop is there, that third loop, that is kth loop. Now in this kth loop again it is going to run for n plus 1 time, and we since it is one time, it will run for n times. So if you multiply it, basically it will be n cube, it will be n cube plus n square plus n something like that. It will be n square, this is n square plus n, and this is n plus 1. So if we calculate it, actually the function would be something like 2n cube plus 3n square plus 2n plus 1, something like that it will come. But we are not focusing actually on this. So we are actually ignoring this. We are only focusing on the higher order. So when we are focusing on the higher order, we will summarize it as n cube. Okay, so this is for the n cube thing, but I hope you are able to understand that how we are tracing out the function slowly one by one and assuming that how it is going to run. Okay, now coming back to the, now we will look for variations of a particular of different type of problems that we may arise in the algorithms. Okay, so let's start with single loops. We'll mostly look out for single loops, and this will be applicable for nested loops as well, just like how we see for the last 3 examples. Okay, so here again it will run for n plus 1 time, and this will run for n, but our focus is actually in this statement. We are not focused so much on how actually it is running. We are focusing on how many times this statement will run, how many times. So it is usually run for n times, so that directly we can say that it's a O of n. And always we have to, sometimes if you're not able to understand why it is O of n, you have to trace it out. So you put the I value. So in this case, until n this I value is less than n, it will keep on running. So you have to check whether 0 or suppose you keep some n as equal to some certain value. So if you put n equal to 5, so it will say 0 is less than 5, correct, 1 is less than 5, its condition will satisfy, that means for loop will run. Similarly for 2 less than 5, 3 less than 5, just like that. Okay, so this is one aspect. And then aspect is here the value of I is incrementing. Here I value is n and is decrementing one by one, and we are checking that whether I value is greater than 0 or not. So here it's reverse. So we are checking whether 5 is greater than 0, 4 is greater than 0, 3 is greater than 0, 1 is greater than 0, like that. Still, so it's a decrementing function, decrementing the value of I. But here still the number of time the statement going to run still will be n times, whatever the value of n here. So it doesn't matter actually when it's either the value is incrementing or decrementing the controlling variable. Here I will be the controlling variable. Because of ith value only we are able to run the for loop. So doesn't matter, and it will still give the same value. O of n, sorry, order of n, it's not theta, it's order of n. Okay, now another interesting stuff is, if we increment here, earlier we are incrementing or decrementing any ith value either by 1 or decreasing it by -1. So but if we increase it by 2, so here we are checking that if I equal to 1 and let's suppose n is 10, so we will say that I is 1, then 1 plus 2 3, whether it's still satisfying. Yes, it is correctly satisfying that I is less than n. Then 3 plus 2, that is 5, 5 plus 2 7, 7 plus 2 9. So instead of running for 10 times, it is going to run for 5 times. So okay, so it is actually running for n by 2 time. So okay, so if you are able to see, it doesn't actually matter whether it is increasing by 2 or 3 or 4. It will reduce the number of actual computation which is going to run for the statement, but we should actually focus on the function. Since the function is still n by 2, we can approximate it as n. Why? The reason will be simple. Here, instead of n equal to 10, if we keep it as n equal to 1 lakh or 10 lakh, if we keep like that, or 1 million if we keep like that, still to run the statement will be approximately half a million, or that is something called 5 lakh or 5 something. Still it is quite a big number, n by 2. That's why we for a bigger number we will approximate to order of n. Similarly here, so if I equal to 1, starting at 1, and the n is equal to 100, if you keep on adding 20 for the ith value, so it will be, the statement will actually run for n by 20. That means it's like 21. So 21 plus 20, 40 plus 20, 60 plus 20, just like that. So even though the n value is 100, this for loop will run mostly for 5 times. That is, if you do 100 by 2, it is equal to 5 times. So this actually function should be n by 20. Still, for approximating, we will turn it as big O of n. Okay, so till now, anyone has any question? Just let me check the chat. Okay, I have shared one link for the same data sheet on which I am trying to explain. If someone is not able to see, again I am putting. Okay, so okay, Tehseen, can you please type in the chat box if you have any question? Or I will just, okay, let's do this. Okay, so if you have anyone question, they can open their mic and they can try to ask a question, because because we are in less numbers, we can see it. So if anyone has question, they can turn off their mic and they can speak. Okay, so I assuming we don't have.
I had a question.
Yeah, Manohar.
Yeah, so any statement with the terminal condition for the for loop, right? No, that incremental condition for the for loop, right?
Yes.
So if it is divided by 2.
Yes, so we will come to that. We will come for multiplication division for sure. That
Okay.
there the equation will be little different. That we will trace it out right now in few
Okay,
upcoming example.
so that will affect this O of n in a different
Yes,
way,
yes,
right?
yes, 110%.
Okay.
Yeah, we will come to that example. So I think 8 example is similar to earlier, so it will be actually run for n by 2 times. Okay. Okay, so now when it comes for nested loops, again, as we have traced out, first we will look for the outer loop, it we will see that how much for the outer loop, that is in this case ith loop, for how much computation it will run. So here it will run mostly for n plus 1 time, and then we will look for jth loop, that is the inner loop. So see, if it is the outer loop is for n plus 1 time, so inner loop will run for n times. Similarly the statement. Now when you come actually for the jth loop, it will run for n plus 1 time, but still the statement, which is our main area of interest, is to run for n times. So actually if we combine them and compute them, at this point we will find that its order will be n square, that we have seen in the earlier example. But here the next example is little different. So what is happening here is, so for the ith loop it is running for n plus 1 time, but here the condition is little different. The condition is until and is j is less than I. So in this case, how should we go for approach? So when you don't have a clear idea, you should usually go for tracing route. So you take I and j value. Okay, so when I value is 0, and then it will go down in the loop, and then we'll check that okay, j is also 0. So when j is 0, the condition will not satisfy, so it will move for another term, the ith term. So when I value become 1, then it will look for j. So j will go for 0, it will run. For 1 it will not run. So again I value go for 2, then the j value will be 0, 1, 2. So here 0 and 1 it is running, but for third condition it's not running. So if you can observe, a pattern we are creating. So for when I value is 3, so 0, 1, 2, 3, so it is running for 3 times, it is not running on the 4th time. So here 1 is there, 1 time. For 1 ith value 1, it is running 1 time. For 2 times, 3 times, that is there. So let's assume that till nth, when it's going to approach n, so it will run for n, and for the n plus 1, sorry, it will go for 0 to n minus 1. I will write it here. Sorry. Yeah, so if the value is n, so it will start at 0, it will go till n minus 1, and when nth is there, the condition will fall, but still it will run for n times. So the pattern here is, whatever the value of I is there, that is the amount of time this particular condition is going to run, this for loop, jth for loop is going to run. And if we combine this all the computation, so we'll find out it will be 0, 1, 2, 3, 4 until the nth. So it is a summation of n times first n numbers. So it for this first of sum of first n numbers, it will be like n equal to n plus 1 by 2, which is equivalent to n square plus n by 2, which is again equivalent to n square. So we can say that approximately this function is going to run for n square. Obviously it is going to run less than n square, but for approximation we are assuming that it will run till n square, because that's this n square plus n, this is the actual time function that we have found, and since the higher order value here is n squared, so we are taking that is order of n square. So we have, I think we have a question. Okay, I plus 1 equal to 21, but in the next step we want 21 plus 20. Okay, so I think you're telling about the earlier function. Okay, yes, what you're saying correct, but in a nutshell I was telling about this. So it's 1 plus 20, so 21, then 21 plus 20, that is 41, 41 plus 20, 61. So if you see the amount of numbers, then it will be 81. So it's starting at 1, then 21, then 41, 61, then 81, that is running for 5 times. Now still the condition will hold true, that for n equal to 100, and we have steps is increasing after every 20 things. So it is for 100, for input of 100 size, it is running only 5 times, so that is n by 20. So because if you put 100 by 20, it will give you 5 times, which is valid. So that's why it's n by 20. I hope it makes clear for you, Tehseen. And I'm sorry, some noise is coming from the background. Uh, okay, so let's back to go to the earlier question that we have seen. Okay, so anyone has problem with respect to this? So we have, since it's not a clear cut, we usually have seen earlier that I is starting with 0, j is starting with 0, so the condition are also equal. But in this 10th question, we have identified that here the loop of j, the jth loop is actually dependent on the value of I. Since it's dependent on the value of I, we have to actually trace it out. So this is called tracing. So we have to trace it out for every I value. We have to trace how the j value is responding. So once this j value is responding, and then we have to find that the pattern. So in this we have found the pattern that it is 0 plus 1 plus 3 plus 4 plus n. So it is giving a sum of first n number, n number. So that's how it is giving to n square. Okay, coming to next question. Okay, so here now we have a p value, external value, and p value is incrementing using this statement. This is our area of concern, and then we have to see how much time this statement is going to run. And we have this condition of p is less than equal to n. Since it's not a clear straightforward, then in this case we have to trace it out. So we have to see that I value and p value. P value is initially 0, I value is equal to 1. Okay, so in the first instance, so when I equal to 1, p will become 1, because 0 plus 1 is equal to 1. When I equal to 2, p will become 1 plus 2. When I equal to 3, p will become 1 plus 2 plus 3. When I equal to 4, p will be 1 plus 2 plus 3 plus 4. So I think you can see the pattern is coming. So till a pattern is coming, but here the question will be till what time we have to stop. So we have to see that till certain k value, that is p equal to 1 plus 2 plus 3 plus 4 plus some k value, where we will find it as this k value is less than equal to, say, is greater than equal to n. If this is satisfied, then we can say that this is the amount of time it is going to run. But if you can see the p value, the value of p that is coming is the sum of first n numbers. So this is the assumption we have made, that at when I value is at some k, we don't know what the k is. When we find that thing, we have to stop. This loop has to stop. So how we can identify that? We identify that when p value is a sum of first k numbers, it will be equal to greater to n. If we trace it out, we'll find that it's actually k plus 1 by 2 is greater than equal to n, and then it is approximately k plus 2 by n, which is equivalent to k square approximately is greater than n, and k value will be, if we put this value here, so it will become root of n. So this particular statement will actually run for root of n time. So we have, okay, so what we have done again is we trace it out. For every I value, we are checking the p value, because this p value is eventually related to the actual condition, which is p is less than equal to n. So we find that till what value of I, this p value will be increased, which is going to be greater than equal to n. So once we so at k point when we stop, we find that it's a sum of first k numbers, and when we expanded it and then find it out that k value is nothing but some root of n value, and so that's why the time complexity of this particular function will be order of root n. Okay, any doubt with respect to this question? If you have, you can unmute yourself and you can ask me. Okay, so I'll continue, and in between you can obviously ask me in this case.
So once repeat, sir.
Sorry, come again.
Once again repeat, sir.
Okay, so this function is actually dependent on the value of p, the 11th function, 11th snippet. So here what we are saying, p is initially 0, I equals starting with 1, and we're incrementing p using this function called p plus I. Now this value is pretty much important because after every computation of p, we are checking that whether p is less than equal to n or not. So once, until and unless this condition is true, the loop will go on. So right now we don't know the value of n, we don't so we have to see that how the value of p is increasing. So what we are doing is we are tracing it out. So we are checking that when I value is 1, we are checking what is the p value. So when I value is equal to 2, we are checking what is the p value. So we are checking that when I equal to 1, p value is 1, when I equal to 2, p value is 1 plus 2, I equal to 3, p value is 1 plus 2 plus 3. Okay, we are trying to see a certain pattern. Our observation is try to understand whether we can get certain pattern or not. So where should we stop? At some kth value, that is when I equal to k, we have to see that this value of p will become so big that it will defy this, it will become p is greater than equal to n. So we have to find that. So what we are saying that, okay, when this kth value reach, we have to see what is the condition of p value. So what we found that the p value will be the sum of first k numbers, is sum of first k numbers, that is 1 plus 2 plus 3 plus 4 plus till k. So now we know that the value of p will be, when the value of p would be greater than n, it will be sum of k numbers. So we have to identify what is that k value. Okay, so we assume that since k we know that at kth value it will be the value of p will be n, so we try to associate here. So we said, okay, 1 plus the first k numbers will be greater than equal to n. Then we actually, this since the sum of numbers, this is the formula that we got, k into k plus 1 divided by 2. If you expand it and if you solve it, it will actually come down to k square, which is greater than equal to n. And when we try to put k square onto the other side, we say that k value will be approximately equivalent to root n. Okay, that's why we are telling this, for this function the order of time complexity will be root n. Okay. Okay, Rohit, you have some disagreement with what the expression that I had? Okay, Tehsi, I believe it's little bit clear here. Once you try it one time on your own, you might be able to understand. It's just that basically expansion part is something you have to take care of. But in any time complexity problem, that you have to understand is the pattern that you are able to find, what the pattern you are extracting from. Okay, so let's go to another example. So here I think Manohar's question will come. Ideally we have checked that when I value is incrementing by either by 1 or decreasing by -1, or it is incrementing by 5, 20, etc. But what if we increase the value of I in multiples or in divisibles, at that time what will happen? So this is something we need to identify. So we have to identify what is the time complexity for this statement. Some statement will be there. So what we have to, we have to trace it out. So what we can do here is I equal to 1, and so we will say that when I equal to 1, it is 1. Okay, at first iteration it will be 1, in the second iteration it will be I into 2, then third iteration will be I into 1 into 2 into 2, which is equal to 2 square, In third iteration it will be 2 cube, fourth iteration 2 raised to 4, 2 raised to 5, like that. But we have to stop somewhere where some 2 raised to k. So what we are assuming that we are assume that this 2 raised to k is greater than n, which is going to defy here. Okay, so once 2 raised to k is there, so let's assume this is the case. That is again coming back to here, the value of I is increasing in terms of 2 raised to square, or say in every time into 2. So it is saying that earlier it was 2, it is 2 square, 2 cube, 2 raised to 4, 2 raised to 5, and we are stopping at some 2 raised to k whose value we don't know. So that is what we want to identify. So this condition will satisfy when 2 raised to k value is actually greater than n. So once it is there, then we have to find the value of k. So to do that, we assume that right now that 2 raised to k is equivalent to n for argument's sake right now, and we will try to find what is the value of k. So if you apply log on both sides, 2 raised to k and log n, here we are applying log. If you apply log, then we will see that it's like k log 2 and log n. So assuming that log is base, if you know the logarithmic, for logarithms a certain base should be there. So in this case you are assuming it as log 2. So in this case this value will become 1. So k eventually will become log n base 2. So the amount of time, number of time this statement is going to run for order of log n base 2. Okay, so the pattern will be like this. First you try to identify till what max value it can go. Then once you identify that pattern, then you try to solve the condition, like this condition. You have to assume certain condition here, that is 2 raised to k is greater than n or not. That's something you have to assume. Once you have this equation, then you have to solve it mathematically to identify what is this k particular value. Okay, so this is for incrementing if you increase the value of I in terms of multiples. In this case 2, if you take if instead of I equal to 2, if it is I equal I into 2, if it's I into 3, the pattern will be k into log n base 3. If it's I equal to I into 4, the k value will be log 20, so it will be like log n base 20 if you go by the same methodology. Okay, now another way how you can see it difference between two functions here is, so here on the right hand side we have a for loop which is incrementing by 1. So the higher I value will be increased by 1 plus 1 plus 1 plus 1 plus like this till certain point, which is basically n. Here the I value will be like 1 into 2 into 2 into 2 into 2 till point it is equivalent to n, right? So it will be like 2, and we assume that it is happening for k times, so we'll say 2k raised to n. Here it is happening for n times, since it is incrementing by 1, so it will say n times. So here directly we can say that it's order of log of n. Here if 2 raised to k equal to n is there, then you have to apply log, and you will find that eventually k is equal to log n base whatever the number here, whatever the multiple that you are giving, that multiple. In this case 2 is there, so we will say k equal to log 2 base log n base 2. Okay, so this is another way using which you can identify the difference between incrementing function, and here it's a multiple related one where you have to use multiply function. Okay, okay, I think it is 14 also is equivalent to same as what we have seen earlier, but let's go for 15th. Here I is divided by 2, so this aspect is equivalent to what you have seen in multiple. that means when, okay, so for that, if you want to trace it out, let's suppose I equal, if I is there, that is n. So for initially it will be n, in the next iteration it will be n by 2 because of this, in the next iteration it will be n by 2 square, in next iteration n by 2 raised to 3, go till a certain point where n is great, n by 2 raised to k, it will go till that time. Okay, here one problem is it should be 0. Okay, so here the equation, here the for loop is wrong, here ideally instead of n value it should be 0. Okay, so this I value will be running till until unless it is greater than or equivalent to 0. So we are here, we have to assume that n, or since it divided by 2, it can also say it is greater than equal to 1. So we have to assume that 2 raised to k is equivalent to greater than equivalent to 1. Till that time this value and n by 2k will be great. If it is greater than 1, the statement will execute. So by solving, if you want to solve it, then it will become n raised to 2k, which is equivalent to earlier, and the k will become log n base 2. So here the time complexity will be order of log n base 2, which is quite similar to earlier function that we have seen here for the multiple function. Here we are just dividing it, here it's just that we are dividing it, but the concept will be remain same. Okay, now this,
I had a question on this division.
Yeah.
So so that conditional check should be I greater than or equal to 1, or it should be greater than or equal to
ideally it should be equal to 1 or 0, both can satisfy, but while solving the equation and to get some understanding, you should assume that this condition should be present, where n equal to 2 by k is equivalent to greater than equal to 1. That's
Okay.
the assumption you are making, which is quite okay, because considering difference between 0 and 1 is not that much.
Okay, so in case of division, we would, for the loop, we would always start from the higher value and get to the least value, right?
Yes, it's like decrementing version of the multiplication. Here when you have addition, you have decrement, when you have, you usually go I plus plus in your for loop, right? So when you try to decrementing, you always start with n. Same goes for multiplication, division as well.
Okay, yeah, I got it. Thank you.
Okay, now another question that we can see here is, for I is greater, I is equal to 0, I into I is less than n, and I plus plus, this statement. So here, instead of tracing out, if you try to do a little bit trickery, you can find that it's basically I square less than n. This is the condition that we have to solve. So we have to see that how many times this condition will be valid. So if you assume here that I square at some point in time will be equivalent to n, so then you can identify that it will, I value maximax can go till under root of, like if we pass this root square to here, so it will become under root. So this statement will run for order of under root x. Sorry. So again, to explain, so if you have to do little bit quickly to understand what is the value for this particular 16th code snippet, we identify that the condition will run for unless until this I square will be less than n. Forget about the increment, since it is incrementing, we don't have to concern much, but this is the condition actually having. So if you just, the same thing, if you try to write in the for loop, you just write it as for I equal to 0, I is less than root n, I plus plus, and statement. This will be equivalent to whatever you have seen in the 16th code snippet. Okay, another thing that we have to understand, with where some people may get confused is here we have two for loop statement, that is one ith and one is jth. These are independent to each other. Okay, so if this ith loop is running for n time, jth loop is running for n time, they are not dependent because they are not nested. So if you have to give the order of this particular code snippet will be the whoever the greatest of these two orders. That in this class, if suppose this is like this, that ith loop is running for n and jth loop is running for n square, then we will say the order time complexity of this particular code snippet will be equivalent to order of n square. Okay, in this case, since both the loops are same, so we will go with n. But if you have a for loop with n time complexity, and this another for loop with, because it is nested, it is go for n square, and you have to say the overall time complexity of this function, you will go with the higher order function. Okay, this higher order function we are going to discuss later in the next session, but this is for something to remember about. Similarly, okay, now here also, if you have to see, we have two functions, that is ith and jth, but here the value of jth loop is actually dependent on p, which is you're going to calculate from ith loop. So if this interconnection is there, then you have to usually you have to go from bottom to up. So that means wherever the condition is present, you assume that first you have to solve this, that is number one, and then you solve this. So how we can see that? So since we have seen earlier that whenever this incrementon is equivalent to j equal into 2, we can say that this statement is going to run for log p base 2, or for now we just say log p for to get a better understanding. Okay, if you can trace it out, is equal, this function is equivalent to j equal to 1, j is less than n, and j is equal to j into 2, which is going to give us log p. That is one. Now here we have to see that this is functions also equivalent to this function jth loop, so it will say log of n. So this p plus plus will run for n time. Now once you have to combine it, so you have to understand that since it is running for log n time, so we have to substitute p value by looking at this. So ideally the value should be log of n. This is the order of this function. So again, trace it back to what we are saying. If we have multiple for loops which are interconnected to each other, that means in this case the value of p, whatever the value of p will be here, it's actually interdependent for the next loop, that is j. So what you have to do is you identify individual for loop for each of these. Okay, my network lost. Okay, can you hear me? Okay, can anyone reply? Can anyone hear me? Excuse me, can anyone hear me? Can anyone reply? Hey, net is working. It's gone. Yeah, sorry, I think my network got disconnected little bit. I'm not able to hear anything actually from second device, that's why. Okay, now I think it came back. Okay, so for this 18th question, as was, since they are interconnected, so what if you try to identify the time complexity of individual functions you can can you see my screen as well? Just let me know such that. Okay, fine, thank you. uh, so since they're interrelated, we have to identify that which variable actually influencing. In this case, p value is influencing the jth value. So if it is if this function is going to run for long n time, so here the actual value will be p equal to log n, and this function is again is going to run for log p time. We just put log n into this value, so it will become log of n. So that's how you will get this time complexity of this function. Similarly, if you have to see for this, if you have to trace it out, this ith loop will run for n plus 1 time, and jth loop, since it is j into 2, it will run for log n time. The statement will run for log n time because we are concerned about this. This will run for n time, this n time, and this particularly run for log n time. So the time complexity of this function will be n log n. Okay, so this is a sum of the function. We have certain function as well to discuss, because already several. I will quickly go through it. So this is analysis of if and while. To summarize here is, while loop is not at all different from for loop. Okay, so these are actually not at all different from for loop. That is something we have to understand, that whatever, so in this I equal to 0, I is less than n, I plus plus there, it will still run for order of n time. Okay, same I equal to 1, I is less than b, a is equal to a into 2, that is it is incrementing by in the multiples of 2. The statement will run for order of log b base 2. Since here instead of n we are keeping b, that's how it will be. So the difference is not that much. But people will little get confused when it comes for the if else statement. Okay, so how we can identify here is, we are skipping right now 20 to 23 because I have to touch one more concept here to quickly wrap up the system. Okay, so here when if and else condition come into picture, there we have to understand a little bit. So what happens is, we see that, okay, this condition, first this condition is that this while loop, we're checking that value of m is not equal to n, and whenever the m value is greater, m value will be decreased by a certain value. If m value is smaller than n, then n value will be decreasing by such value. That's how it is working. So to trace it, for tracing out this kind of function, if else function, you have to sometime play with the values of the variables. So here the variables are m and n. So considering m is greater than n, so think of a values which is actually greater than n. So let's say m is 6, n is 3. Since this condition is satisfied, so m will be 6 minus 3, which is equal to 3. In the next loop, since this 3 is not less than 3, it will come to here, and here we will find a 3 minus 3 equal to 0. So in this 6 and 3 condition, the number of time it will run is 0. Okay, when m and n are actually equal, then this while loop itself will not run. Now let's try to take a bigger m value. So if we take m is equal to 16 and n is equal to 2, okay, then if you try to reduce the value, it will find that m value reduced by 2 only. So it will be 14, 12, 10, 8, 6, 4, 2. So if it is running for, okay, so actually it is running for 7 to 8 times. Okay, so for a particular value. So at this time, at this point, we can safely say that given a value of m and n, it is too much dependent on a value of n. So how much it is decreasing. So it is so for considering m is 16, so it will usually, and n is 2, so it will go by order of m by n. Okay, so in this case, since the m is 16 and n is 2, so we will say that this particular function, this particular n, because it is running more, it will run for order of m by n, and you have to simplify it. Usually it will be again in the order of m, because we have seen earlier that whenever order of n by 2 or order of n by 20, it's usually considered to order of n. So here also, if we giving order of m by 1, it will be equivalent to order of m. Okay, so what are the type of function that we have seen till now? This is summary of what we have seen. So we have seen constant function, that means it is going to run one statement, so we will say it's constant, order of 1. Order of log n we have seen when j is equal to j into 2 condition we have seen, or j equal to j by 2. This kind of condition we are saying when the values either increasing or decreasing. Such kind of situation we have seen logarithmic, we have seen linear, we have seen quadratic, cubic. Exponential we haven't seen, we will see in the next part of in the next session. So different type of functions are there, but what exciting part here is this is called class of function. We're going to discuss about this next session, but here we will see that which value is actually greater and less than which of which. That means constant will be less than log n will be less than root of n of n is less than n log n is greater than n, just like that. So this class of function is there, and mostly we want most of the algorithm should lie in this space. Okay, this we want to lie our function in this space, but we have multiple function which lie in this space as well. So in algorithms we trying to avoid any function whose type complexity is exponential. We try to make it polynomial. Okay, so that's the area of research that we have for particularly for algorithm area. We're going to discuss more about this in the next session, but to summarize, here we will have different class of function, and that is something we have to observe, identify, and try to make our algorithm more fast, because 1 will be the fastest, log n will be little slow than 1, but it will be log n algorithm will be more faster than n square algorithm. So that is something we are trying to identify through our analysis. Okay, and to understand that why this 2n or n square is bigger than log n or n, we can take one example. So when value of n is 1, log n 0, n value is 1, n square is 1, 2 raised to n is 2. When value of n is 2, log n will be 1, considering its base is 2, n will be 2, n square will be 4, 2 raised to n is 4. When value of n is 4, it will log n will be 2, just a minute, n will be 4, n square will be 16, and 2 raised to 4 will be also 16. But things start from here. As the input size increase, we will understand the value of how this particular function actually behave. So when the value is 8, log n is 3, n is 8, n square is 64, 2 raised to n is 256. Value of 9 maybe 3.1, assume approx, n is 9, it's 81, and 5 112. So you can see the difference between these two functions, and then you can assume the difference between n and 2 raised to n, and the difference between log n and 2 raised to n. So as the input size is increasing, when the input size increase, computation will also increase. That's something we have to keep in mind while solving the algorithm. So one food for thought: do you think that n raised to 100 is greater than 2 raised to n or not? That is something you need to think about and try to see whether it's actually true or not. If it is true, till what extent? If it's not true, till what extent? Okay, Yeah, Manor, I think you have want to say something.
Yeah, I had a question. So, when for the exact if-else statement, what is the actual time complexity?
At,
Uh,
see, there will be no exactly actual complexity. It will be always approximation, because here we are
so
doing
I'm
an.
saying like if-else statement, will it take like O of one, or does it depend on the condition by itself?
It depends on the condition. So, for example, okay, I will try. I didn't had this example. So here it is saying that if the value is greater than n, sorry, if the value is greater than n, you print this statement. If the value value is, say, n value is less than 5, you print the statement. If n is greater than 5, then you print the statement which is going to be order of n, otherwise it is order of 1. But we are mostly focused on whenever if this condition doesn't hold, so else condition will hold, right? So at that point of time we have to see which among which of the condition, if and else, which is giving more complexity, and then we will say that overall, in overall, or this functions, this particular algorithm complexity will be O of n.
Yeah. So basically, and my question is, you said for the for loop, it is the time complexity the for loop begins with is n plus one, right? Like that only for if statements. In case n is lesser than 5, let's consider n square is greater than or equal to 5. If it's like that,
Okay.
so in that case,
in
the if
that in that
statement.
case, only the order of 1 will satisfy most of the cases.
So the if statement by itself will take order of 1.
If statement will still will take order of 1, yes.
Whatever happens inside is a different thing.
Yes,
The
but the
state,
but again we have to check whatever inside. For example, this in else statement we have another for loop. So for example, instead of this, if I remove print from print here and try to put this for loop in this if condition, then it will be order of n, because if n is greater than 5, which will be true for most of the in almost all the cases,
okay.
you will
So
tell.
the if else conditions output or the time complexity output will be the worst case or the highest order of whichever is there. If for
Okay.
the
Yes. So there will be something called as best, average, and worst. This is something we're going to discuss later, but we have to consider all the three cases.
okay.
So in this case, the best case would be order of 1, worst case will be order of n. And if you think that n value will be mostly greater than 5, assume that then average will also be order of n, according to this logic that we are having for this algorithm test.
Okay. 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 I got you. Thank you.
Yeah, so I think, yeah, that's the end of the session. uh, this video is going to upload in YouTube, and NPL team is also going to give this video link to you. So if you have any doubts and all, I just shared this this sheet with you all of you in the Google chat, okay, earlier. So if you still have a doubts, in the next session we are going to discuss actually about this best, average, and worst case. We will go actually into the notations of time complexity. There we can discuss more in more in detail. Okay, so let me stop the recording.